We'll be looking at hypothesis testing and confidence intervals in this proportion, so much of what we'll be covering will be very familiar. The only difference is in this section we'll be working with two proportions instead of a single proportion. Let's go ahead and go over some of the notation that you'll see and some of the formulas that you'll need. First of all, you'll see p hat 1. P hat 1 is basically the proportion estimate, that's why we have a hat on top, for the sample 1. Now usually this is going to be something like min, and then p hat 2 would be something like the proportion of women. So a lot of times when I'm working these problems, I'll put, instead of a 1 and a 2, I'll put an M for men or W for women, or P for placebo and T for treatment to help me keep track. But usually they're labeled 1 and 2, so it's important that you keep track of which group was 1 and which group was 2. And of course, because these are proportions, you put the number of successes over the total number of outcomes. So you'll see p hat 1 and p hat 2. You'll also see p bar. This is going to be the averages of the p's, so this would be x1 plus x2 over n1 plus n2. Now it's important that you just don't average the two numbers that you get here, but you actually combine these, because based on the denominator or the sample size, if they're not even, this will change. It's not a weighted average, but it'll be more toward the p2. Now if p bar is x1 plus x2 over the sum of the n's, q bar is going to be 1 minus p bar, because of course p bar and q bar have to sum to 1. So these are some of the values that you'll see while we're working. We'll also have a test statistic. So our test statistic, and this is when we're doing hypothesis testing, of course. This is a z statistic, so we'll be using our normal tables, and on our calculators we'll be using t distributions. This is kind of a long way to write this out, but it's p hat 1 minus p hat 2 minus p1 minus p2, and this will come from the hypothesis test, and it will usually be equal to 0. We'll talk about that when we get to a particular problem. And then we have this huge denominator. This is going to be p bar q bar over n1 plus p bar q bar over n2, and all of this including the denominators under the square root sign. So that's the test statistic that we'll be using when we have hypothesis testing. Now the way we find the p-value and everything, none of that has changed. And then we have the general form for a confidence interval. So for our confidence interval, we'll have our point estimate. Remember, the form never changes. So point estimate plus or minus our margin of error. Now when we're talking about our margin of error, we have to include the fact that we're working with a z distribution. So this is going to be p hat 1 minus p hat 2 plus or minus z alpha over 2. Alpha is the amount of error that we're willing to have. And then this should look familiar from up above. This is p bar q bar over n1 plus p bar q bar over n2. So this is a general form of the confidence interval, point estimate plus or minus margin of error. And this is the specific confidence interval that we'll be using for the difference of two proportions or comparing two proportions. Now what we're interested in testing when we're doing our hypothesis testing is the difference in the proportions. So some hypotheses that you'll see are something like HO versus HA. Now remember, for the HO case, the difference is always equal to 0. So this means the proportion of population 1 minus the proportion of population 2 is equal to 0. Now if you think about this, this basically means from this P1 minus P2 equals 0. If I add the P2 to the other side, this is basically testing to see that they're the same. So this is checking to see that they're the same. Now the alternative hypotheses, there can be a lot of different ones. Let's go ahead and look at P1 minus P2 is less than 0. So again, if we look at P1 minus P2 less than 0, I could add P2 to both sides and I'd get P1 is less than P2. So this alternative hypothesis is actually checking to see whether the proportion of population 1 is less than the proportion of population 2. So that's one hypothesis set that you'll see. Another one could be HO versus HA again. Now our null hypothesis is always the same. It's always the equality case. Now here, let's go ahead and look at P1 minus P2 is greater than 0. So as usual, this first one means that the P1 and P2 are the same. I'd add the P2 across. Now this one, if I take P1 minus P2 greater than 0, if I add the P2 across, I'd get P1 greater than P2. So basically what this is saying is the population proportion for population 1 is greater than that for population 2. So for instance, we could say the number of accidents in the city is greater proportion-wise than the accidents in the country or something like that. You're comparing two. Now the third case is the not equal to case. So this would be HO versus HA. And as usual, the equality always goes in the null hypothesis. And then I'm checking to see if there's a difference, to see if they're different. So let's go ahead and look at the HO here. Again, this is our equality case, P1 minus P2 equals 0. I'd add the P2 across and I get P1 equal P2. And then down here for the not equal to case, I would go ahead and add that P2 across and I get P1 does not equal P2. So this would be checking to see if they're different. There's not one that's more or less, they're just different, they're not equal to. Well, for the not equal to case, we can also talk about a confidence interval. So we can also test with the confidence interval. So remember, our confidence interval was the point estimate plus or minus margin of error. So if you recall, the confidence interval P hat 1 minus P hat 2 plus or minus our margin of error. And that was Z alpha over 2. P bar Q bar over N1 plus P bar Q bar over N2. Now it doesn't really matter what this is made up of right now, just remember that it's margin of error. And I'll also show you some shortcuts on the calculator to help you with these calculations. So what we're looking at here for a confidence interval, again, is that point estimate plus or minus our margin of error. So this piece right here is our point estimate. Point estimate of the difference, and this is our margin of error. Okay, so if we end up with a confidence interval that's all positive, so some positive number to some positive number, and the way that this would look in its confidence interval form, it would be a positive number less than P1 minus P2 is less than some other positive number. What that's telling me is this difference is always positive. So P1 minus P2 would be greater than 0. Greater than 0 because I have positive values here. I'd add the P2 across, and so I would end up with P1 is greater than P2. So if I end up with a confidence interval that's all positive, that's what this is telling me, is that the difference is positive, and then when I solve for the difference, P1 is greater than P2. Now, when I have a confidence interval that's all negative, a negative value to a negative value, that's telling me that the difference is always negative. So P1 minus P2 is less than 0. I'd add the P2 across, and what this tells me is that the P1 is less than P2 if the entire interval is negative. Now what if I have an interval that goes from negative to positive? So I start out with some negative value and I go to a positive value. So I have a negative number to a positive number. Well, what we have here, because I'm going from negative to positive, it's not all negative, or sorry, it's not all greater than 0, it's not all less than 0. In fact, it contains 0. So this interval contains 0. And because it contains 0, that means that they could be equal. P1 and P2 could be equal. So I have this case. P1 minus P2 could be less than 0 from this piece. P1 minus P2 could be equal to 0 because I have to go through 0 to get from a negative number to a positive number. Or P1 minus P2 can be greater than 0. So I have all three of these cases that could happen. So what this case is where I would fail to reject HO. And that's when P1 minus P2 equals 0. And the reason I have to fail to reject HO is that This could be negative, it could be positive, and it could be equal to 0. I don't have evidence to show that they're different. So if we look at all three of our alternatives, we have the less than 0, whoops, this one should be not equal to 0. So we have less than 0, greater than 0, or not equal to 0. And because this contains all three, I can't say that it's any of these. Okay, so this would be our fail to reject case. Over here, if they're all positive, this is when I would decide to reject, because it's all positive. Because these are all negative, I would choose to reject here as well. And we're also going to be using, the p-value approach to hypothesis testing to check these, but the confidence interval comes into play as well. Just a quick review. When we're doing hypothesis testing, remember we have critical values, and we also have these scores that we use when we're having confidence intervals building. So we have three common critical values, or levels of confidence. We have 90, 95, and 99%. And there's others as well, but these are our common ones. Okay, so for 90%, that's 1.645 plus or minus. Now this is our critical value we'd use for hypothesis testing and also with our margin of error. 95% would be plus or minus 1.96, and 99% would be plus or minus 2.575. So let's go ahead and look at our first example, and we'll set up one of these problems from start to finish. Okay, for this example, we are going to be looking at two different groups. We're going to have a treatment group and a placebo group. So the treatment group would be the group of people who actually received a medication, and the placebo group would be the group who didn't receive the medication, but perhaps just a pill, like a sugar pill. So for the treatment group, we're given that N1 is equal to 160 and X1 is equal to 40. And for our placebo group, we're given that N2 is equal to 300 and X2 is equal to 60. Okay, let's go ahead and use a significance level of 5% here. Oh, that reminds me of here on top of the critical values. These are used for confidence intervals and for two-tailed test. So two-tailed hypothesis test. If we have a single-tailed test, these values will change. And we'll just have to do a quick curve sketch, a little picture to see what's going on there. So we're going to use an alpha level of 5%. Now what we want to test is whether or not the proportions are the same. So basically what this is saying is the number of people who were successfully treated in the treatment group were 40 out of 160, and the number who were successfully treated in the placebo group were 60 out of 300. Now what we want to do is we want to test the hypothesis that HO, the proportion for group 1 minus the proportion for group 2 is equal to 0, versus the alternative that they're not equal, meaning one is larger than the other. We're not saying which one is larger and which one is smaller. We're just saying one is larger than the other or different from the other. So that's step 1. Step 2 of hypothesis testing is we state our level of significance. Step 3, we go ahead and calculate our test statistic. Now when we go through and calculate our test statistic, it's kind of a long one. So we kind of need to summarize some of our values here. So for our test statistic, we have Z equal, now we have P hat 1 minus P hat 2 minus, in parentheses, P1 minus P2 from our hypothesis test. And this is all over the denominator. And this is P bar Q bar over N1 plus P bar Q bar over N2. And all of this is square rooted, the numerator and the denominator. So it looks like we need to find quite a few values here. So let's go ahead and look at P1, P hat 1. P hat 1 is going to be from this group, in this case my treatment group, N1. So P hat 1 is going to be X1 over N1. So it'd be 40 over 160. Now this rounds really nice to 4 times 4 is 16, so 40 over 160 is 0.25. Now if it didn't round nice, we'd want to leave it in fractional form, so that way we wouldn't have rounding error. P hat 2 is going to equal the values for my placebo group, which is the population 2, 60 over 300. 60 divided by 300 is 1/5, which is 0.2. And again, if this was not a nice decimal, we wouldn't round it. We just leave it in fraction form. Okay, we also need P bar and Q bar. So P bar is going to equal x1 plus x2 over n1 plus n2. So that would be 40 plus 60 over 160 plus 300. So 40 over 60 would be 100. Or sorry, 40 plus 60 would be 100. And then 160 160 plus 300 would be 460. Now this one we're probably going to have to round a little bit. Let's go ahead and pop open our calculator. 100 divided by 460. So 100 divided by 460. And let's go ahead and take this out to 3 places. So let's do 0.217. Now Q bar is going to be the complement of that. It's 1 minus P bar. So in this case, 1 minus 0.217. So 1 minus 0.217. And that's equal to 0.783. Now these are all the numbers that we're going to plug in here to calculate our test statistic. So Z equal P hat 1 is 0.25, so we have 0.25 minus 0.20. Now P1 minus P2 comes from my null hypothesis. And if you notice, we have here P1 minus P2 equals 0. And for our work that we're doing, this will always equal 0. Now P bar was 0.217. Q bar was 0.783. And that's over N1, which was 160. Plus the same thing again, but a different denominator for this fraction would be over 300. And all of this is square rooted in the denominator. So let's see what we get for our test statistic. Now when you plug this into your calculator, you have to be very careful because we have a lot of layered fractions here. So let's go ahead and start with 0.25 minus 0.20, and we want to make sure that's in parentheses. And then I'm just subtracting 0, so I don't really need to include that. And then we'll have divided by the square root, 0.217 times 0.783 divided by 160. That's this first fraction right over here, plus 0.217 times 0.783 divided by 300. Now that's the entire radical, so we can go ahead and arrow out of that and hit enter, and that should give me my test statistic, in this case 1.24 if we round it to 2 places. Just make sure you look at the rounding directions that are given to you in my math lab. So this is my test statistic. Now if I'm using the p-value approach, we're going to take this test statistic and calculate the p-value. So here we are, step 3, test statistic. Step 4, let's go ahead and calculate the p-value. Now some of the questions in your homework will ask you to find a critical value and a z-value, and those really don't relate because you usually only do one or the other. But remember, you can just go ahead and calculate that score real quick, or look at the values from the table and just kind of input that. You don't need it to find your p-value. So we're going to use our test statistic z equal 1.24, and we're also going to use the fact that this is a two-tailed test. Remember, if we have a two-tailed test, we double our p-value. So this is my standard normal distribution with a mean of 0. Now remember, a p-value is a probability of getting a value as extreme or more extreme. So that's why I'm shading this highlighted area right here. Now our calculators will help us find this value. So if we go to, under distribution, second DISTR, we're going to go to normal CDF. The lower bound in this picture is 1.24. The upper bound is going off toward positive infinity. We don't have an infinity key, so we just put in a very large number here, like 100,000. My mean is 0 and my standard deviation is 1. And so this will be half my p-value. I take this times 2 because it's a two-tailed test, and there's my overall p-value that we'll use here. And that would be these last couple lines. Okay, so this p-value that we found here, first of all, and we can use our tables too, will be 0.1075, we'll say. And remember, we have to double it, so p equals 2 times 0.1075. So I get a p-value here of 0.2150 if we were to round that to 4 places. And I get that the same thing here, so if I round here. Now again, you can use your tables as well. Step 5 would be to make a decision. Now remember, we can only make 1 of 2 decisions. We can reject or fail to reject HO. We'll reject HO if P is less than or equal to alpha, and we'll fail to reject HO if P is greater than alpha. Well, for our case, P is equal to 0.2150. Alpha was 5%. And it's pretty clear here that P is greater than alpha. Therefore, we would fail to reject HO. So there's our decision. Now let's go ahead and look at our summary or our conclusion. We failed to reject HO. That means our original assumption that they were equal has support. So way back up here, we're failing to reject this. So this is where the evidence is supporting. It's not supporting the fact that they're different. So it looks like to me, when we look at these two treatment groups, one of them was 25% success, the other one was 20%. It doesn't really look like those are significantly different enough to say that one is better than the other. So here's our conclusion or our summary. The data supports the conclusion that there is no difference, and I should say no statistical difference, between the treatment and the placebo. Okay, now that's using the p-value approach. Okay? Now let's also do the same problem, but we're going to calculate a confidence interval. So same problem, confidence interval. So remember, with our confidence interval, that was p hat 1 minus p hat 2 plus or minus z alpha over 2, and then we had our p bar q bar over n1 plus p bar q bar over n2. So this is grouped together. So p hat 1, let's go ahead and look back up at all of our summary values here. P hat 1 was 0.25. P hat 2 was 0.2. So I have 0.25 minus 0.2 plus or minus. Now my level of significance was 5%, so alpha of 5% creates a z-score of plus or minus 1.96. Now p bar and q bar, again we're going to come and look up here, was 0.217 and 0.783. Over n1, which was 40. Plus, got to extend out this radical sign, 0.217 times 0.783 divided by my second sample size, which is 300. Whoops, this sample size is incorrect over here. That was x1. We wanted n1, which was 160. Okay, so 0.25 minus 0.2 is 0.5. Plus or minus, and now we need to go ahead and plug this into our calculator. Again, we have to be careful how we do this. We definitely have 1.96 out front, so let's start with that. 1.96 times the square root of 0.217 times 0.783 divided by 160 plus 0.217 times 0.783 divided by 300. Now this is my margin of error, so I get 0.07909, etc. So let's go ahead and throw that in to our calculated values. And again, that's my margin of error. So if we round this to 2 places, let's say, this would be 0.07, or let's go to 3 places, 0.079. So again, point estimate is 0.25 minus 0.2 is 0.05. Let's be more careful here. Plus or minus 0.079. So my left end point would be 0.05 minus 0.079 is less than the true difference in the proportion is less than 0.05 plus 0.079. Okay, so for my left end point, we'd have 0.05 minus 0.079. So we have negative 0.029. It's less than or equal to the difference. Now remember, the difference looks like now it could go from negative to positive. So now let's take 0.05 plus 0.079. And I get 0.129 out of that, so that makes sense. Now, what's happening here is this interval goes from negative values to positive values, and it crosses 0 in between. So it's saying this difference could be negative, it could be 0, which is in between, or it could be positive. So from here, since 0 is since 0 is contained in the interval, we would fail to reject HO. It appears the treatment and placebo groups are statistically similar. Now there's a lot of different ways to say these conclusions. So that's an example of going through every single step. Now remember, sometimes you'll be asked for the critical z-value, sometimes it's not relevant. So let's go ahead and come back up here and look at some shortcuts. These 6 steps that we used here. Let's go ahead and look at our raw data and look at some shortcuts in our calculator. Now we haven't ever looked at these before because I wanted you guys to get a nice big understanding of the p-value approach to hypothesis testing, but this is going to give us an idea of some shortcuts. So let's go to the stat menu and over here to tests. Now we have a 2 proportion, so here's a 2 proportion z-test. So that's what we're looking at because we're using the z tables, the standard normal tables, and we don't have 1 proportion but 2. So I'm going to go to the 2 proportion z-test. Now let's go ahead and fill in our values here. These values that were here by default from some other test that I did. But we can see x1 is 40. We can see here that n1 is equal to 160 over here. x2 is equal to 60. And n2 is equal to 300. So again, all these values are given to us in the tables. Now what this is asking for here is, are we looking at a 2-tailed test, a left tail, or a right tail test? Now remember, this was a 2-tailed test because we were looking for the not equal to case, so I make sure that's highlighted. Now if I want to change it, I would just arrow over and hit enter, but I want the 2-tailed test. I don't really need to see a distribution drawn of the normal curve. We just go ahead and hit calculate. Let's go ahead and paste this into our lecture and see how it compares. So we're going to compare some values here. So for instance, if we look at the test statistic, we see that the test statistic is 1.24 rounded, and we can see that that's what we have here too. This is my p-value, 0.2156. Let's go ahead and scroll down, and you can see our p-value here is 0.2150, but it's very, very similar. The difference is there's a little bit of rounding going on here, so this is actually a little bit inaccurate. There's no rounding up here. So you can run this entire test using this on your calculator, but you still need to write in the step 1, step 2, step 3, step 4, but your calculator gives you the output. So just as a quick little reminder, this is the test statistic, and this is the p-value. And remember, this is the reminder that this is a two-tailed test for alternative hypothesis. So this is a nice little shortcut. Now down here for my confidence interval, there's a similar shortcut. So let's go ahead and go back to stat, over here to tests. And now I don't want to do a test, but I want to do a confidence interval. So I'm going to scroll up this time, and I'm going to get to a 2 proportion z interval. So I'm going to fill in my same values. I'll have 40 over 160, 60 over 300. My confidence level here, though, is not 99%, it's 95%. So let's change that to 0.95, 95%. And calculate my values. And what this is going to do is it's going to give me a confidence interval, in particular a 95% confidence interval. So let's go ahead and compare that. Okay, so if we compare our confidence interval, we can see it's very, very close. My left endpoint here is negative 0.0309. That's very, very close to negative 0.029. My right endpoint is 0.13094, and this is slightly lower, 0.129. And again, the error comes into play with the interval I have because I rounded values up here. I rounded the 0.217 and the 0.783. Now, can you use this on homeworks, quizzes, and exams? Absolutely. But make sure that you remember to go through all of your steps and draw a conclusion, because you can't shortcut any of those. They're very important. So get used to using this 2 proportion z interval to build a confidence interval, and then also for the other one with a 2 proportion z test, where you can pick a two-tail test, a left tail, or a right tail test. Sometimes when you're working problems, you won't be given all of the information directly, but you'll be able to calculate it indirectly based on what's given to you. Let's go ahead and look at this example. For this example, we have a survey, and 28% of single women surveyed that they definitely want to have children. Now if you notice, they're already giving us the percentage here, so we don't know two things here. We don't know the number of single women asked, and we don't know the number who responded that said they definitely want to have children. So let's go ahead and add a little bit more information here. 28% of, let's say, 220 single women surveyed said they definitely want to have children. And then we also know that 26% of 275 single men said they definitely want to have children. So what we're looking at here then is we have a percentage and we know our sample size for each group. And what we want to do is to construct a 99% confidence interval. That will estimate the difference between the proportions. Now, if my math lab or your problem doesn't give you like who's P1 and who's P2, usually it's the first one listed as P1. So we'd call P1 the single women, P2 would be the single men. So construct a 99% confidence interval that will estimate the difference between the proportions. So when I start a problem like this, I want to look at what I'm going to call P1 and P2. Now, we're going to use our calculator on this one. So when you use your calculator and you're trying to find a confidence interval, let's look at what information is needed again. We go to Stat, Tests, and remember we're trying to build a 2-sample proportion confidence interval. So 2 proportion, normal distribution is Z, int stands for interval. So that's the one that we want here. Let's go ahead and see what information they need. They need to know X1 and N1, X2 and N2 and the confidence level. Now, we don't know X1 and X2 though. We do know the sample sizes. We have to work backward on this to be able to come up with the X's. So let's go ahead and work with P hat 1 first of all. Well, we already know P hat 1 is 0.28. What we don't know is how many people responded out of the 220 that said they wanted children. So X1 in this case would be 0.28 times 220. Now, if this gives us a nice integer, that would be good, but if it doesn't give you a nice integer, you'll just need to round, because you can't put in, so we have 0.28 times 220. So we do get a fraction and a decimal here. I'm not going to be able to put this into the calculator as 61.6 because the calculator is thinking you need to have the specific number of people. We can't have, in this particular case, 61.6 people. So we'll have to round that. But let's go ahead and calculate P hat 2 first. So P hat 2 was 0.26. We don't know the number of men who responded positively out of the 275. So here we have X2, that's X2 right here, is equal to 0.26 times 275. Okay, so let's go ahead and calculate this one as well. See if we get an integer or a decimal. 0.26 times 275. So we get 71.5 here. So again, we can't put these numbers into the calculator. You could use these numbers if you were going to build your confidence interval using the formula working by hand, but our calculator won't let us do this. So for this one, let's go ahead and round this one to a 72, and this one we'll go ahead and round to a 62. And these are the numbers that we'll put in our calculator. So going back, we go to Stat, over to Tests, and we are looking for 2 proportion Z interval. So here, X1 would be 62, and if we can't put a 61.6 in or we'll get an error, and that was out of 220 women. X2 was 72, that's our rounded value, out of 275 men. Our confidence level for this problem, if we want to look backward over here, it's a 99% confidence interval, so I'll put in 0.99, and then we hit calculate. So this will give me my confidence interval directly. You can also work this problem by hand, and it doesn't matter to me what method you use, but you have to make sure you show your work. So here we can see that we have our confidence interval then goes from negative 0.0838. So let's go ahead and write this like as we would see it written. Is less than the difference, which was P1 minus P2, which is less than 0.12376. So let's think about what P1 minus P2 was. This was the same. 1 was women. So let's go ahead and write women here. And then 72 was men. So if we want to interpret this, P1 was women, P2 was men. So women minus men, the difference was negative. It was less than 0. Notice that it could have been equal to 0 as well, because it's in this interval from a negative to a positive. Or the difference could have been also positive from over here. So you can see it could have been 0, negative, or positive. So since it can be all three of these, 0 is in the interval, is the important key here. So basically we can't draw a conclusion. So no conclusion can be drawn. We could fail to reject HO if we were doing hypothesis testing. So we can't really draw a conclusion on this. So what that would do then is kind of go back to the idea that they could be equal to 0. P1 minus PM, women minus men, could be equal to 0. So there's really no conclusion that we can draw here. So there's no evidence of a gender gap. Now, the hypothesis that's actually being tested here is P1 minus P2 equals 0 versus P1 minus P2 does not equal 0. So because 0 is in the interval, basically we'd fail to reject HO. So if we fail to reject HO, that's basically saying there's no evidence that there is a true difference. So there's no evidence of a gender gap here. So if you're doing this one by hand, you can use 61.6 and 71.5. But if you are not doing this by hand, you've got to use the 62 and the 72 as integers, because you cannot put decimals in your calculator using this particular function, because it doesn't really know what to do with the decimal, since you can't actually have 61.6 people. Okay, let's go ahead and look at one last problem. For our last problem, we're still going to be talking about a confidence interval and relating the idea of the confidence interval to a two-sided hypothesis test as well. Now for this one, we are given that a total of 55,279 people were surveyed. They also tell us that 50% were male, and then of course by default then 50% were female. And what we have here, 28% of women that were surveyed said that female bosses are harshly critical. And then we surveyed men, and we found that 26% of men said female bosses were harshly critical. So what we want to do is we want to construct a 95% confidence interval. And basically what we want to do is to estimate the difference between the proportion of women and the proportion of men who said that female bosses are harshly critical. And then what we want to do is to figure out if the proportions are statistically significantly different. So in this particular case, since we started with 55,279 and we were told that 50% are men and women, if we want to use our calculator for this, we need to figure out what 50% of this number is. So to start with, we want to talk about P hat 1, which I'm going to call P hat women, and P hat 2, which is the same as P hat men. The 1 and 2 make it hard for me to keep track of, whereas men and women make it a lot easier. So for this particular group, for the women, I already know that 28% was my proportion. For the men, I know 26% was my proportion. I don't know how many women were asked, though. I just know that it's 50% of the total. Now, if you notice here, this 55,279, it's an odd number. So that means I can't take half of it and get a nice integer. I get 27,639.5. So I'm going to round this to 27,640. And since each were half, I'm going to call both of these 27,640. Now remember, I have to do this because in my calculator I have to put in integers because it doesn't understand a 0.6 of a person or something like that. Now to find the numerator here, I would just take 0.28 times 27,640 because I want 28% of that total. So let's take 0.28 times 27,640. And so that's, again, going to have to be rounded, 7,739. 7,739. And then we'll do the same for men. So we have 0.26 times 27,640. And so for this one we have 7,186. Okay, now we have a 95% confidence interval. So let's see if we have enough information to do this test on our calculator. So we go stat, tests, and we want to have, whoops, let me try that again. So we go stat, tests, and we go to the 2 sample proportion because we're trying to build a confidence interval. Okay, so now we know x1 was 7739, n1 was 27,640, n2 was 7,186. And remember, you can do these by hand using our formulas we had as well. And then for my n2 I have 27,640 as well. Now our level of confidence is not 99%, it was 95%, so we need to make sure we adjust that. Hit calculate, and then let's go ahead and paste this into our lecture so we can use it for comparison. So basically what we have here then for our confidence interval for the difference is 0.012 to 0.027. Now notice, this is the only one we've looked at today that's all positive. Okay, so since this doesn't have 0 in it, it doesn't have negative values, it's all positive, that's telling me something about our claim. So HO versus HA here is what we're actually looking at. We're not doing a full-blown hypothesis test, but I'm looking at P of women, the proportion of women minus the proportion of men equals 0, because that's always my case. Equality is always 0. And then I can look at PW minus PM. Now in this particular case I'm trying to see if there's a difference, so I'm looking at not equal to 0. So my proportion for this runs from 0.01261, whoops, that's a 1, less than P sub women minus P sub men is less than 0.02741. So this entire interval is positive. So when we say positive, we mean greater than 0. So this would look like P sub W minus P sub M is greater than 0. Now if we move this across for comparison, I'd add the P sub M across. That means the proportion of women is greater than the proportion of men who would say that female bosses are harshly critical. So the conclusion that we can draw here then is this confidence interval, because it's entirely positive, supports the conclusion that a higher percentage or a higher proportion of women say female bosses are harshly critical. And that's because the entire confidence interval is positive. So those are the types of conclusions that we can draw from a confidence interval. Now remember, this is not a true hypothesis test. We haven't run everything here, but because this entire interval is positive, that leads me, I could reject HO in favor of the alternative hypothesis that there really is a true difference. And because it's positive, I can say that this is the direction of the difference. So the steps for calculating confidence intervals, the hypothesis testing, the p-value approach, all of that is unchanged from section to section, all those steps. What changes are our test statistics as well. So feel free to learn how to use your calculators for these shortcuts. One thing I want you to be sure of though is on a test or a quiz, you need to make sure you show all of your work if you want to receive credit. If you have any questions, please feel free to bring your questions to class, stop by my office or the Math Center as well. Good luck.